I'm good, Dave. You want to introduce him?
It's up to you. Just turned 6, we'll wait until 6:01.
I should use that mic, right?
Yeah, you
Yeah.
can.
Okay, welcome. A little smaller crowd tonight than I expected, but you know, a little snow, that's the way that goes. So anyway, this is inventory that we built on 1990 inventory that I did way back when. And to go through and kind of compare the water quality to them. And we wanted to look at a whole variety of different things. And so we got Elmo, Amy, and Kevin up here that are going to each do a little bit of section on it. And feel free to ask questions after each person gets through. We'll take a break for questions and then we'll move on to the next one. So with that, I think, Elmo, you're up.
Is that louder? Oh, you can't tell here. All right, I'm going to use the microphone because I think it helps project into the microphone that's up there so people on Zoom can hear us a little better. Hi, I'm Elmo, and I'm going to talk about the glacial geology of Burnett County. That's going to set up the sediments and the type of materials that the groundwater is flowing through. Amy's going to talk about groundwater movement and groundwater susceptibility to contamination, and Kevin's going to talk about groundwater quality here. I'm with the Wisconsin Geological and Natural History Survey, and then I've got a co-author up here, Mark Johnson. He's a professor in Sweden, and he did a lot of work in Wisconsin in the early 2000s, and he helped us produce the map that's on the wall. That's a map of the glacial geology of the county. There we go. Okay, I do want to set up just the project goals, the products we're making and presenting tonight, and then the timeline associated with the project. We're here, we were hired by the county to help provide an inventory and analysis of groundwater resources in Burnett County at the county scale. So there's a copy of the map on the table. That's the scale that we're trying to generalize the whole county to. So the products we're providing are sort of an overview of the county or a very generalized version of the county, sort of baseline information, if you will. It's not necessarily site-specific information, at least the products Amy and I are making. And then identify areas where groundwater is more vulnerable to contamination from land surface activities. Amy's going to talk about that. The products that we're making for this project include improving the location, our understanding of the location of wells, which are associated with a construction report that tells you something about the geology. So prior to this study, the DNR knows where wells are, but they kind of come in the middle of a township and range oftentimes, and they're not even at the location of the actual well. So there's some work to improve that. We made a glacial geology map. That's the part I'm going to talk about. Amy's going to talk about a water table elevation map, depth of water, groundwater recharge, depth of bedrock, some cross sections, and a contamination susceptibility map. So Amy's going to have a longer presentation, and then Kevin's going to talk about some well water analyses that maybe some of you sent to him or some of you online had sent to him. Timeline for the project. We've been doing this since 23. So in about half of 23 and all of 24, we were collecting data and putting together preliminary results. This project, that phase of the project ended in December. So we had preliminary results to share, but everything we're going to talk about today still has to go through a review process, internally and externally. and then will ultimately be available for publication sometime probably early 26. So it's still preliminary. We're still a little early, but the lion's share of the work is done. Okay, what's the Wisconsin Geologic and Natural History Survey? Quickly, that's where Amy and I work. Kevin, I'll let Kevin introduce where he works. We're all associated with the University of Wisconsin-Madison Division of Extension. And the Geologic Survey is the state's geologic survey. So you may have heard of the USGS. That's the Federal Geologic Survey. And then each state has its own geologic survey, which is the primary archive for geologic information for that state. It's been around since the 1890s. It's not a very large organization, 30 staff members. Some of them work on groundwater issues like Amy. Some of them are glacial geologists like myself. So that's looking at the sediment above bedrock. Then we have bedrock geologists, GIS staff, IT staff, administrators. Like I say, we're responsible for the whole state geology. So 30 isn't a very big number to cover all that. We do the best we can. And then there's our website. Because we're a state organization, all of our information is public. It's all available on our website. All of our reports, all of our maps, all of our databases are free for download. And if it's not available on the web, there are some databases that you can call and have access to.
In and out, maybe not look so much at the screen and look.
Go this way?
Yeah, like,
I always look at the screen for some reason. You know, it's right there.
I'm sorry.
I was hoping it might help, but it doesn't. All right, given that, sorry, I'm focused on Zoom, I'll face the screen. I think that helps with the audio online. I'm going to talk about late Wisconsin Ice Age or glacial sediment and glacial deposits in the state of Wisconsin. Can't do it without looking. So to do that, we have to think about Wisconsin in about 18 to 20,000 years ago. Wisconsin would have looked like this. Ice in Canada, centered around Hudson Bay, works its way down to the lower 48 and sort of ends in Wisconsin here. And if we zoom in on Wisconsin, right, the world would look something like this at the maximum extent of that glacier, where most of the ice for Burnett County is coming out of the Lake Superior region. And there are times when we're completely covered in ice. And then there are times as that ice retreats, we're still impacted by the ice. And there's some ice that comes into Burnett County from the south. And there's Minnesota ice, basically, ice that's coming out of Minnesota. So ever since the Pleistocene, there's been Wisconsin and Minnesota have been converging on Burnett County. All right, so 23,000 years ago-ish, this is what the Burnett County would have looked like. And up over in here, right, we would have been completely covered in ice coming from the Superior Lobe. Maybe 15-ish thousand years ago, ice was retreating and parked in sort of Ashland, Bayfield County, Douglas County area, still melting and still impacting the St. Croix Riverway and St. Croix lowlands. But then again, there's this little piece of ice that comes in from Minnesota that works its way in the St. Croix Valley and blocks up the St. Croix River and creates a proglacial lake. It's called Glacial Lake Grantsburg that you might have heard of. Okay, so when we're at the end of a glacier, if you go to the end of a glacier today, or if you're at the end of a glacier in the Pleistocene, you're at the point where that glacier is melting, right? So even though it might be moving forward or retreating, when we think about glaciers moving forward or retreating, that's a response to how much ice is forming in Canada or in alpine systems at the top of a mountain. But as that ice then moves either down the mountain or to the south, it reaches warmer areas and it starts to melt. So the ends of glaciers are associated with a lot of water. And that can take and sediment. That can take the form of streams, or it could be captured in these proglacial lakes in lowlands out in front of the ice. If we're sitting under the glacier, I just want to show sort of some typical pictures of the types of sediments that are deposited by glaciers or right in front of the glaciers, because those are the types of sediments that we find in Burnett County, and they make up the aquifers or the aquatards, or they prevent water from infiltrating into the groundwater system or at least delay it, but may cause some more runoff. Those are things that Amy is going to sort of talk about more. But glaciers are good at picking up sediment. They're very bad at sorting sediment. So when we see sediment deposited by glaciers, it tends to be everything from boulders down to clay, very poorly sorted, lots of pebbles, and pretty finely, a lot of fine grain component to it. When we're out in front of a glacier, if we go look at river systems out in front of glaciers, those tend to be really sandy and gravelly. So they might have a lot more, the fines have been transported by the streams further away. The heavy material is left behind by the streams. And when that sediment is buried, that's stuff that makes a pretty good aquifer, right? You can pump water out of those sands and gravels. And then the lakes, right, are sort of basins that catch those fine grained materials often. And we get a sedimentation that looks something like this, where clay, silt, clay, silt, we get a rhythmic sedimentation of silt or clay, but all of it is usually the finer grain component. So again, if that's in the subsurface, not a great place to pump water out of. If it's at the surface, it's going to reduce the amount of water that reaches the groundwater system at that, wherever that sediment type is located. Okay, so one of our goals is to make geologic maps. We have, like I said, we have people working on bedrock maps. We're people working on the glacial sediment map. This is the map that shows the distribution of finished products. So places where you can get a map of the county at that scale, 1 to 100,000. Blue are maps that are published on our website. Green are areas that we're currently working in. Price County is highlighted because I'm also working over there. But Burnett County obviously over here. It's going to turn blue in about another year, right? Will be published and available online. I do just want to talk briefly about what kind of data do we use to make these geologic maps. So we're using high resolution topographic information, LiDAR. It's airplanes flying, lasers. The laser shoots through the vegetation, hits the bottom of the ground, comes back up, and you can get a very high detailed 1 foot, a data point for every foot through the vegetation, and see what the landscape looks like without trees, without forests. This is not stuff that we're making. This is public data that either the federal government or county government has put together. And it's really high resolution. So I've zoomed into the Crooked Lake area, and you can see braided stream patterns from the Pleistocene or from the last ice age, and old shorelines along the lake. And it's a very helpful tool for compiling geologic maps. We use the USDA soil maps. So the US Department of Agriculture has already mapped the soils. You can think of the soils as the first 3 or 4 feet, and then the maps that we're making are maybe the next 30 feet. They're really just the superficial geology below the agricultural soils. But they do indicate in their maps what the parent material of the soil was. So I've colored what they thought was meltwater stream sediment as pink. I've colored the glacial sediment as green, and lake sediments as blue. Modern stream sediments are yellow. And that's a pretty good first guess at how we would characterize the sediment, and matches pretty well what we come up with. We're also using water well construction reports. This is the distribution of water wells. You can see that there are some places where there's not a lot of water wells, so usually low wet areas. You can see some places that have a lot of water wells, usually around the lakes, there's a lot of wells. So imperfect distribution, but a lot of them. And the well drillers write a report and submit that to the DNR that includes the type of material they think they're going through. They're kind of blasting through it though. They're flushing it out with water, or their because their goal is to put a pipe in the ground with water out of it, not to collect the geologic samples. So pretty good data set, pretty helpful. The only data set really though that gives us information of what's at depth. So we combine all that with our own field observations. We'll go to any gravel pits or natural exposures that we can find and get access to. And then we collect our own samples, take that back to a lab in Mount Horeb. We have a facility, photograph it, document it, subsample it, and carefully describe the sediments or bedrock types that we're going through. And we do that either with a small rig that has a 2-inch pipe, really cheap, or relatively cheap, I should say. And we'll go about 30 feet just to check that map. Or if we're combining this with a groundwater study like this, maybe we'll want to go to 1 or 2 places where we're concerned or where we know there's thicker sediment, and we can go 300-400 feet. And that's a little more expensive, and it's a bigger rig on a 4-inch pipe, and very similar to the equipment they use to drill wells. But again, we're going 20 feet, we're pulling all the rod out, we're collecting the sample. We're going 20 feet, we're collecting all the sample, taking it back to a lab, analyzing it. And this is the distribution of cores. 2 of the deeper cores for this associate in Burnett County. There's a few more of the shallow cores up here that I don't have displayed, about 80 of the shallow cores. So that, combined with the soil data, combined with the LiDAR, combined with the well construction reports, gives me a pretty good sense of what the geology is. And we end up with a product that looks something like this. So I'll just go through what we can see on the map from across the room and what some of the sediment types look like, and then turn it over to Amy here pretty quick. All right, if the green Spooner Hills over here in the southeast part of the county, and some of the sediment up here that we've mapped as green, that's a glacial till or a red glacial till that's a little bit sandy, but still has quite a bit of silt in it. That's deposited when we're completely under ice. So that's material from the northeast. It's going over granites, metamorphic rocks, igneous rocks, has a lot of iron in it, and not a great aquifer, not a great place to pump your water from. This green portion here, right near Grantsburg, that's another till. That's that sediment from glacier that came in later from the south and brought in sediment from Minnesota.
What about the 70 on there?
70 is right here. And there's a copy of the map. If you're in the room, there's a copy of the map, and that map I'll be leaving that copy behind. So town of Grantsburg, somewhere right in here. That's like Crex Meadow. That brown is wetlands. Gray till at the surface, pretty silty, hard to infiltrate for water to recharge the groundwater system. There. These pinks and buff colors are all areas of meltwater stream sediment. So areas where rivers were flowing as the ice retreated out of the area or reoccupied the St. Croix Valley, sands and gravels, lots of infiltration. Also, if they're at depth, good places to get water. These are centimeters. So 3 of these is about an inch. The blues fading into the purple this way are this younger Grantsburg Lake that sits at the surface, the one that showed when we showed where the ice was around 15,000 years ago. So that's a lake that forms because the ice blocks the St. Croix Valley when it's sitting here at the Pine City or in the Grantsburg area. If we went at depth there in that area and went a little deeper, we might hit another lake. This is a so-called glacial Lake Lynn. And but that one only occurs in the subsurface. It does outcrop in the St. Croix Valley. When you're going down to the boat launches, you get about halfway down and water will be coming out of the side of the valley. It's hitting this clay. And if you went over there, you might find some of this clay. So that's one thing that's only in the subsurface. There are also some older glacial tills in the subsurface. This is what Wisconsin looked like during the last ice age or that late Wisconsin. That's the dark green line up here. These lighter greens sort of in front of that, and these purples represent areas where there were glaciations here prior to the Lake Wisconsin. So Illinois in age, 125,000, or even older than 800,000 years ago. So the Wisconsin was glaciated many times in the last 2 million years. The Lake Wisconsin one, it was the most recent and is one we're usually thinking about because it's the stuff that is at the surface for most of the state. If we took a cross section, if we cut the earth and looked at it from the side, Amy's going to talk more about this, but this is the Trade Lake Township, and this is like right in here. And we have that gray till at the surface in this dark green. But then if we drill through the sands and gravels, which are pink, we might find other tills down there that are either that are part of these older advances, River Falls Formation and a few other formations. This is that Lake Lynn clay, this blue. But when you look at these cross sections, we drilled one hole and we drilled another one near Grantsburg. That's it for the whole county. So that's the only geology, that was collected by a geologist. The rest of these lines are wells, and we use those well construction reports. But again, there's not a lot of them. And so we don't always know how connected these layers are. And even along this line, we're pulling from almost a mile on either side just to combine that all together and represent a schematic version of what you might expect to be down there. And these are really for illustrative purposes that it's very variable. In some places, you might have a lot of sand before you hit a till. Other places, you might hit a lot of tills and have to maybe go a little deeper to get to water. Okay, next steps for the glacial geology. Finish the core descriptions. We're still analyzing some of the cores. We have enough of the analysis done to make the map, but we archive all the information, so they'll be split, photographed, and subsampled, and that'll all live in Mount Horeb. We'll write a report for this. That has to be reviewed externally, internally, and then we'll publish that sometime in 2026. But if you can't wait to read about the geology, the glacial geology of Burnett County, I refer you to Polk County's report that Mark Johnson, the guy from Sweden who joined us, wrote in 2000. And he was really interested in those lakes, and he has a lot of information about Burnett County hiding in that report too. All available on our website, free for download. And there's the core that we collected in August. That's sitting in Mount Horeb, and that's what I'm going to be start working on here in February. So thanks for listening. Again, there's my email. I'm at the Wisconsin Geologic Survey and always available for information. Yes.
Say available for download, available for sale, also in print.
The question was, we're going to repeat questions too, so people online can hear. The question was, is it available in hard copy for print? No, we used to sell hard copies, but when the internet came and we put on our website free for download or $20 for a hard copy, our sales plummeted, and to the point where we weren't making enough money to pay somebody to manage the sales anymore, right? So I'm a fan of hard copies of maps. I think they should be hard copy, but we do have some links on our website about how, if you want a hard copy, how you can send it to Kinko's or one of those places and get it printed.
There was a question in the chat, the slide before the Trade Lake cores, asking about the Danbury area and the soil types, I think.
Up in Danbury's, like up in here or over here?
Yeah, along the St. Croix River.
Yeah, along St. Croix River. So the question is, what are the sediment types along St. Croix River? There are some glacial tills at the surface, but most of it is sand and gravel of older levels of the St. Croix that were basically draining the glaciers. So again, the glaciers have a lot of water. They also carry a lot of sediment. And so a lot of the St. Croix Valley is filled with post-glacial sands and gravels from that meltwater stream sediment. So mostly sandy, except down sort of in here. If you go about 50, 60 feet, you're going to find that red clay right in the subsurface. That red clay stops somewhere where the lakes start. If you drill where there's lakes, we don't find that red clay in the subsurface.
And red clay was the paint line. They made for paint for barns.
Paint for barns, and then were they mining using that one for bricks too, or was that more of the Grantsburg
I
clay?
don't know.
There was a brick mine. There was a brick yard up here too, and We have a publication from the early 1900s about lake clays because the brick industry was local and very lucrative back in the early 1900s. And so we sometimes pull that one out because where the brick yards were, where all the periglacial lakes were, that's where the clays were.
Any other questions in the room here? Otherwise, anybody on the chat or Zoom, you can unmute and ask a question. They say our well is 365 feet deep through to granite. Does that sound true? 365 feet deep through granite.
I'm gonna refer well questions to our well experts. So I would save that question for Kevin at the end. Kevin, do you want to answer that now?
I don't know why they'd go into granite in this part of the state, but there's other parts of the state where wells have to go into the granite because there's so little sand and gravel above it.
And then it probably isn't granite, it's probably a basalt. It's a similar igneous crystalline rock, and those rocks typically don't have a lot of water in them, so you have to go deeper to get enough water to pump, right? But the well driller might call it granite.
Okay, so Elmo did a good job setting us up to understand the geology. That's going to be helpful when I go through the groundwater mapping results that the survey did. My name's Amy. I'm a hydrogeologist with the Geological Survey where Elmo works also. So I'm going to give a little bit of background on groundwater to set us up here. Talk a little bit about some specific goals of this mapping, share the preliminary maps, and then wrap it up with a summary. So what is groundwater? So groundwater is going to be any water that's in between the cracks, the pores, in between the rocks and sediments that are beneath our feet. And when we have a rock or a sediment layer that can store and transmit water really well to our wells, no pun intended, we call that an aquifer. And aquifers provide drinking water to about 70% of the residents of Wisconsin. So it's a really important source for drinking water. I also have up here a diagram of the water cycle. This tells us all water is connected. That includes groundwater as well. So it can tell us where our groundwater comes from, and ultimately it starts as precipitation. So when it rains, that water can either go back into the atmosphere. Actually, that's where both or most of it ends up. Some of it can run off into our lakes and our streams. But some of it can actually infiltrate the ground and move past the soil root zone and make it to our water table. So let's look at that a little bit closer. What's the water table? That's just going to be the top of our groundwater. And so what it does is separates two different zones. You have the saturated zone on the bottom. That's where we have the space in between the rocks and the sediments completely filled up with water. And then above that, you have the unsaturated zone that can have air and water in between the spaces. So again, when it rains, some of that rain can make it past the soil root zone and recharge to our water table. Knowing that, a couple of things I want you to remember. Most of this recharge is going to be happening during the spring snow melt. And that's when a lot of the plants are dead, so they're not going to take up as much water. So more of it can make it to the water table. And then the second thing is that the water table can move up and down depending upon how much precipitation we're getting. And so it's important to remember that it's not static. let's talk about how groundwater moves. So most things move from a high potential energy to a low potential energy. We know that surface water likes to flow downhill, right? So that's what I'm showing on this diagram. You can see that the black contour lines there are connecting equal points of elevation of the land surface. So that's like a topographic map. And you can see we have runoff flowing into the stream, which is a low point in the landscape. And you can see that those blue lines are at a right angle to those black lines. That's going to be important to remember. So when we're thinking about groundwater, it's the exact same thing, except we're thinking about the surface of the water table instead of the land surface. So now the black lines on the bottom are representing equal points of the water table elevation. And again, you can see the flow direction. Groundwater likes to flow from a high point in the water table to a low point in the water table. And again, at right angles to those black lines. So if we know our groundwater levels, then we can understand a little bit how groundwater flows. And then I also want to point out, if you look at the very bottom of this blue diagram, I've labeled a recharge area. So that's where we have water entering the groundwater system, flows more downward, and then you have it flowing along a flow path here. And eventually it's going to reach what we call a discharge area. This is usually a low spot in the landscape where you have groundwater emerging back at the land surface. And so you can see here it's a stream, but it could also be a lake or a wetland as well. And so this means our groundwater and our surface water are connected. I want to talk a little bit about lakes as well. So a lot of our lakes are partially fed by groundwater, but I want to talk specifically about seepage lakes because these are really common in Burnett County. And they're a little bit different than what's called a drainage lake. That's what you see on the left-hand side. With a drainage lake, you have a stream inlet and an outlet where water can flow in and out. But the key difference with the seepage lake on the right-hand side, you can see that there's no stream inlet or outlet. And this can be a problem because this means that the only way water can get out of the lake is by evaporation or back into the groundwater system, which are really, really slow. So if it rains a lot, the lake level will rise, but then it's going to take a very, very long time for that to come back down because there's, only a few options as to how it can actually get out of the lake. And because of this, areas around these seepage lakes tend to be pretty vulnerable to flooding. So now let's talk about the materials that store our aquifers again. Elmo just covered the superficial aquifer, which is the focus of this project, but this just puts it into context a little bit. These are the aquifers that we have in the state of Wisconsin. You can think of this as a cake where the sand and gravel aquifer is the frosting on the top that's made up of loose sediments. As opposed to the bottom three layers, which we'll call our solid rock cake. So those are made up of solid rock. So in Burnett County, what we have present is this crystalline bedrock aquifer on the bottom. That's not a really good aquifer. We have the sandstone and dolomite aquifer on top of that, and then the sand and gravel on the very tippity top. And like Elmo said, the sand and gravel aquifer makes a really good aquifer where the materials are really sandy, but not so good where they're more clay rich. So that's why it's important to understand the geology. Okay, Elmo covered this already with the project goal. One of the more specific goals of the project, though, was the second bullet, identifying areas where groundwater is susceptible to contamination from the things that we do on the land surface. And so I'll be going through a number of maps, and I'm going to use these red arrows to indicate whether an increase or a decrease on the map will correspond to an increase in the susceptibility of groundwater to contamination. And so I'll talk about this map more at the end, but this type of map only considers the sensitivity of the landscape, and it's not including any contaminant sources or land use. So just keep that in mind as well. What are some questions that these type of maps can answer? Elmo told us what our aquifers are made of. After this presentation, I hope we can answer some of these other questions. So what are groundwater levels? What direction is it moving? How much groundwater enters the system in an average year? How deep do I have to drill to get to groundwater in different parts of the county or to reach bedrock? And then why are some areas more prone to groundwater flooding in the county? This is an overview of what I'll be covering. The well construction database is the main source of data for all of the maps I'm going to show. I'll then cover the water table map, depth to water, groundwater recharge, and depth to bedrock. And then the last two things on the bottom are going to really summarize everything and bring it together. The cross sections help us better understand what things look like underground. And then the susceptibility map is going to be made from a lot of these other maps. So it will be a good way to round everything off and bring it all together. Okay, Elmo touched on this already, so I won't spend too much time on this, but like I said, the well construction reports are really our main source of information. And so we just want to verify as best we can where these wells are on the landscape. And the county worked on this with training from our staff, and we're able to identify about 7,000 wells across the county to improve the location more to get it more accurate. And so you can see there are some areas where we're going to have less data, but even in the areas where we have data, there are still uncertainties. Either, you know, things can be recorded incorrectly on the report, or maybe we don't know exactly where the well is on the landscape. So just some things to keep in mind. Okay, so let's first talk about the groundwater levels in Burnett County. This is the water table elevation map. This is read similar to a topographic map. So the contours are representing water table elevation, and the solid lines are a 20-foot contour interval, and the dashed ones are a 10-foot interval. And the closer together the lines are, the steeper the slope of the water table. So just to orient you, you can see it's a really steep along the St. Croix River. And it actually is lowest right along the St. Croix River at about 780 feet. And then the highest point in the water table is kind of in the southeast corner here at about 1,220 feet. So I made this map by using the well construction reports. They record the water level on those reports. And that's the distribution of them again. But even in the areas where we don't have a lot of wells, we still have a really good idea of where the water table is, because Burnett County has so many lakes and streams. And that tells us where the water table is, because that's essentially where groundwater comes back to the surface. So back in 1998, when the first water table map was made, there were only about 900 wells to make this map, and I had a lot more than that. So I was able to make the map a little more accurate, which is good. So if we zoom in a little bit, I can show you that a little bit more. This is in the Trade Lake Township. You can see the black lines are from 1998, and the updated lines are in blue. So a little bit different. And again, we can show groundwater flow direction by drawing arrows at 90 degrees to the contour lines. And so you can see, depending on where you are, it's going to be flowing in a different direction. And knowing where groundwater is flowing, what direction it's flowing, can be really useful when trying to figure out where to put a well or a waste disposal facility or anything else that's going to have the potential to impact our groundwater. So once we know the groundwater levels, we can make a depth to water table map. And we do this just by subtracting the elevation of the water table from the land surface elevation. And you can see the map on the right, the darker the blue, the closer the water table is to the surface. So you can see across much of the county, the water table is very close to the land surface. This is good news when it comes to drilling a well. That means you don't usually have to drill very deep in a lot of the county, but this can be an issue with flooding. So if the water table is really close to the surface, we get a lot of rain, that water table can rise and cause some issues. And that kind of ties into what I mentioned earlier about the seepage lake areas being very vulnerable to flooding. Why do we care about this in terms of groundwater susceptibility? Well, if we have a shallow depth to the water table, there's going to be less time for contaminants to break down or be filtered out before they reach the water table. So if you can think about it as the depth to the water table also indicates how thick that unsaturated zone was that I talked about. And there's a lot of chemistry and biology that can go on in that zone to kind of help slow things down. But when it's really shallow, we don't have that. So just keep that in mind. Next, we've got groundwater recharge. Again, this is how much water is entering the groundwater system on an average year from precipitation. So this is ultimately what controls our groundwater levels. This map was made using an average over the time span of 2012 to 2022. The county average during this time is about 7 inches per year, but you can see it varies across the county. It kind of has a area where of low recharge here of less than 4 inches on average. And then in the northern part of the county, there's an area where it's greater than 10 inches on average. And a lot of that has to do with the soil type, and I'll talk about that later. In terms of groundwater susceptibility, groundwater is going to be more vulnerable where you have areas of high recharge. If you think about it, that's where groundwater is entering the system. And so along with that water, it can carry contaminants. So the higher the recharge, the more vulnerable. So what can we expect for a range in the recharge? On the left, you can see it was a wet year, 2014, an average of about 13 inches of recharge. On the right was 2021, that was a dry year, 4 inches on average. So this just gives you an idea of how this can change depending upon how much precipitation we're getting. And I'm showing precipitation here on this bar chart. So in gray is the total precipitation over that 10-year period. The teal is the recharge in inches on the y-axis. And you can see whenever we have an increase in precipitation, the increase in recharge corresponds to that. And that makes sense because, again, recharge and precipitation, that's the source, or precipitation is the source of our groundwater recharge. And we got these groundwater recharge estimates using what's called a soil water balance method. Basically, it tracks the fate of precipitation. Where does it go once it hits the land surface over every single day in this 10-year period? So the inputs are, it's taking into account precipitation and temperature, but then also 4 other inputs that help us figure out where it goes once it hits the land surface. So number 1, land surface elevation, that helps us know where surface water runoff should be routed in the model. The second is land use or land cover. That's important to consider because at a more developed area, you're going to have more runoff, and then different plants, of course, take up different amounts of water in the soil. The other 2 inputs are related to the soil type. So on the left is how much water the soil can store. On the right is the essentially the runoff potential of the soil. So the A's are going to be your sandier soils with a low runoff potential. And then the Ds are going to be your more clay-rich soils with a higher runoff potential. And we see that in addition to elevation, normally we have high recharge in high elevation areas. The soil type is another key piece to that. And that makes sense when you think about it. You have a sandy soil, water is going to flow right through that. If you have a clay-rich one, it's going to be a lot slower. So when we compare the recharge results to Elmo's map of the glacial geology, it actually makes a lot of sense and the patterns look similar. So what type of bedrock do we have in Burnett County? I'm going to talk about this a bit just because we're going to see the depth to bedrock map in a second. And I kind of covered this already. So again, it's the bottom two layers that I talked about earlier. So we have that basalt in the dark purple. That's a volcanic rock. Sometimes people call it trap rock. You may have heard that term before. In the northern part of the county, we have some shale and sandstone. And then this yellow stuff is another sandstone. So this is some of the solid rock you could expect to hit in Burnett County. This is for the same kind of area in Northwest Wisconsin, mapped at a much coarser scale. So when you look at individual counties, it's not super detailed or helpful. So we did make a county scale map for Burnett County, which is shown here. And here, the darker the color indicates shallower depth to bedrock. And so you can see across most of the county, depth to bedrock is greater than 100 feet. Another way to think about it is the sediments that Elmo talked about are greater than 100 feet, typically can be up to 350 feet thick or so in Burnett County. You can see there are some areas where bedrock is close to the surface along the St. Croix River. And there are some spots in the southern part of the county too. In terms of groundwater susceptibility, so if you think about this as the thickness of those sediments, if you have thinner sediments, there's going to be less time for contaminants to be filtered out or slowed down before they make it to the water table. So the shallower the depth to bedrock, the more susceptible groundwater will be to contamination. We made this map using the data points shown here. There aren't a lot of wells, like we were talking about earlier, that hit bedrock in Burnett County, which is unlucky for us in making this map. There's about 284 of them that we were able to use. So we also supplemented with some other data sources using the statewide soils data set. We know from previous mapping projects, there are some areas where our geologists have observed bedrock outcrops at the surface. So this is where you can actually see the rock at the land surface. We also used about 900 points from Minnesota's depth to bedrock map across the river. So that way we could constrain the elevation better in Burnett County along that state line. So once we have the elevation of the bedrock surface, then similar to how we made the depth to water map, we subtract those elevations from the land surface to get the depth. Okay, so now I'm going to show a couple of cross sections, and Elmo actually covered a lot of this for Trade Lake already, but this is for town of Roosevelt. So the geology over there is a little bit different. This is in the southeast part of the county. And you know, it kind of looks like we have mountains here in Burnett County. And I just want to explain that, you know, we had to exaggerate this vertically so that we could actually see something. This is what it would actually look like if I had it up on the screen, so it's not super helpful. So if we're looking at the town of Roosevelt, you can see we have bedrock in the gray, and then our superficial aquifer sediments are on top. Again, the sands and gravels are in the pink, and Then I have that sandy till in the green. That was the red till that Elmo showed you a picture of. You can see they're pretty heterogeneous, these lenses. And like Elmo said, we don't really know how well connected these are, where we don't have a lot of well data. But these are a nice way for us to visualize what's going on underground. You can see we also have the elevation of the water table, and we can get an idea of groundwater flow direction. Here it's from east to west, and then we have local flow towards our surface waters labeled in the blue on the top here. Elmo showed you this one of Trade Lake, so I'm not going to spend a lot of time on this one, but I just want to point out, because we're going to be zooming into Trade Lake again later to look at susceptibility. The presence here of this siltier till or more clay-rich till, this was the gray till that Elmo showed you. This is going to provide some protection of the aquifer below it, because we know that water flows slower through more clay-rich sediments, right? That's going to differ from the eastern part of Trade Lake over here. Okay, so now I'm getting to the susceptibility map. Just to orient you a little bit about what these maps show. This is our statewide susceptibility map. So the red colors are highly susceptible and the greens are less susceptible. So these type of maps consider the geology and kind of the characteristics of the land, but again, they don't take into account our contaminant sources or land use. So these maps aren't showing where groundwater will or won't be contaminated, but it does give us an idea of, you know, where the landscape is more vulnerable if land use were to change, for example. So what it's really conveying is how easily can water flow from the land surface to our water table in these areas. This is if we zoom in on that map into Burnett County. It's not super helpful because it's made from generalized statewide information. And so we use more specific information to make a map specifically for Burnett County. And that's what you see up on the screen now is our susceptibility map for Burnett County. You can see the darker the color, the higher the susceptibility. So we have our highly susceptible areas kind of along the St. Croix River in the northern part of the county and in stream valleys in the southeast over here. And overall, the county has very high susceptibility when you're thinking about it compared to other parts of the state, just because of the conditions that I talked about with the water table being so close to the land surface, and then the really sandy soils in some parts of the county. So I'm just going to quickly zoom in on Trade Lake again to talk about a little bit about the inputs, and we've seen the inputs already throughout this talk, but this just is a nice way to visualize what's going into this map. So we have the depth to water, our recharge, depth to bedrock, and the superficial sediment type. And so when I made this map, essentially we're adding up components of these four, and the ultimate pattern then is what you see on the right. And if you can remember when we looked at the cross section, this kind of makes sense because we had that clay-rich till in the west that's providing some protection of the aquifer. But in the east, it's more sandy. We have higher recharge rates, and we have a pretty shallow depth to water table over there. We also have the bedrock kind of near the surface in the southeast corner. So these types of maps are helpful for helping us understand how the geology and the landscape can impact our groundwater quality. But of course, you need a contaminant source as well. And I think this sets us up well to talk about the water quality. That's what Kevin will be covering. So in summary, this was an updated groundwater inventory that we did for Burnett County. It's going to be really helpful in answering a lot of the questions up on the screen here, but also any other questions that come up related to our groundwater. And Elmo's gonna be writing his report on the glacial geology. I'll be writing the report on the hydrogeologic atlas of Burnett County. So this will have a report that I'll be working on now, the map plates, as well as the digital data for all of the maps that we've covered so far. So expecting that to be available in 26 sometime. If you want to read about the hydrogeology of Bayfield County, that will look similar. We have that up on our website right now. Okay, and so I will take a pause here if there are any questions before we go over the well water quality sampling results. Okay, you guys have any questions?
As I understand it, generally, this area is getting wetter, is that expected? Do you have any? Follow that.
That's a good question. So for folks online, the question was, are we expected to get more precipitation here over time? And how would that affect the groundwater system? Right?
Yes.
So we have not looked at any trends over time in precipitation specifically for Burnett County, but I know on campus there's the Wisconsin Institute of Climate Initiatives. I think I got that right. They actually have data on their website to show whether precipitation is increasing or decreasing over time in different parts of the state. And I believe they have that level of detail for each county. So I would recommend checking that out. I know when I'm trying to remember if I looked that up or not. I can't remember off the top of my head what the predictions were for Burnett County, but of course, if it was predicted to get wetter, that would affect the water table in Burnett County. We would expect it to rise, and flooding issues could perhaps increase, but I'm not sure what's predicted for Burnett County in particular. You're welcome.
One thing that you could look at is the groundwater monitoring well at the Webster Ranger Station. And that still has a traditional ups and downs, but the downs are higher than they used to be and the ups are higher than they used to be as well. So the trend is gradually up over the course of the last 50, 60 years. But who knows what the future is going to bring. And I think there was a question about can you access the constructor reports, the well constructor reports? I'm assuming you can.
Can you access the well construction database? The well construction reports, that is publicly available. I'm sure Kevin will get talk about that.
Yeah, it's those you can access on the DNR's website. They have a nice tool where you can search by township range section or by your address. So if you just Google well construction database Wisconsin DNR, we could take you there. Otherwise, if you need help finding your well construction report, any of us would be happy to help with that.
The other one was, what if we don't get snow and how would that affect groundwater recharge and that sort of thing?
So if we get less snow, that's going to probably result in less groundwater recharge. If you remember at the beginning, I talked about how one of the main sources of groundwater recharge mainly happens during the spring when you have all that snow melting. It's a big pulse of water into the groundwater system. And so if we have less snow, it may be that it's not all released in such a shortened time period. I guess if there's also, if it's rain happening, we're still going to get recharge if you have rain rather than snow. It'd just be a different form. I think that answers your question.
Laura says you are amazing, and then also asks, what about pesticides, etc., along the river farms and hog farms and Grantsburgs? What are their effects on water quality?
Yeah, so Kevin will get into the water quality, but I don't believe there were any pesticides tested for this project. And so that's something that might be recommended depending upon the situation. But of course, it all kind of depends, I guess. Do you guys have anything to add to that? Okay, yeah.
I think we'll answer Zach's question after Kevin's presentation, just because it's about wells.
Okay.
And then maybe how much pollution is running into the river. So you guys didn't really look into that.
Yeah, so we didn't look at surface water runoff in particular. We're more focused on groundwater. So yeah, I don't really, yeah.
Right, that was the last one, so.
Mhm. Sorry.
So while Emily's getting my presentation up, I'll just do a quick introduction. My name's Kevin Masarek. I'm the director of the Center for Watershed Science and Education. Our center is a partnership between UW-Madison Division of Extension and the College of Natural Resources at UW-Stevens Point. Our center does a lot of work with private well owners, communities statewide, doing kind of large scale well water testing projects. And the real benefit is twofold. One is that all of the individuals on private wells who submit samples get a much better idea of the water that they're drinking on a daily basis. But two, by testing as a large group, as a community, we get kind of a snapshot in time of groundwater quality in that area. And by working statewide, we've created a large data set that I always tell people really paints the picture of groundwater quality in Wisconsin. So I just want to extend my gratitude before we start, because any of the information that I show would not be possible if it weren't for people like yourselves taking advantage of the opportunity to test and submit a sample. And you may say, well, why wouldn't anybody want their water tested? Truth is that not everybody does. So we're extremely grateful when people are participating in these programs. Just a little overview about how the well water testing worked. Burnett County reached out to landowners. They selected participants or wells, and they sent, I don't know how many letters you sent out, over 1,000, probably 1,300 letters. And there was about 506 landowners that agreed to participate or submit a sample. We mailed sample kits and instructions to those individuals. Most of you here probably participated in that. Hopefully the instructions were clear, relatively simple. You mailed it back to us, and approximately 451 of those kits were returned and analyzed at the UW-Stevens Point Water and Environmental Analysis Lab. So that's where the information that I'm going to present is coming from. And my goal is to help you better understand what those results mean, and then help you better understand Burnett County groundwater quality. So if we look at the maps of the data that I'm going to illustrate, they're all going to look very similar to what you see here. We're looking at, obviously, throughout tonight, we've been looking at Burnett County, and the light area in here is Burnett County. All of the maps are going to be similar, but they're also going to include the locations, as well as a little bit of information about the concentration that was measured. So on this map, it's showing the sample distribution, and the sample color, the color of that dot corresponds to how many samples we would have received from that quarter section, or that 40-acre parcel. So the blue dots are one sample. In some cases, we received 2, maybe 3 samples from the same 40-acre grid cell. In those instances, we'd be displaying the average concentration. This map correlates pretty well with the maps that Amy and Elmo showed, showing the well construction, where are wells actually located. Obviously, it's easier to get samples from those areas where there's a lot more wells.
But there's some gaps that correspond to areas where there's just not a lot of individuals that have property or have wells accessing the resource. Amy covered the groundwater movement as well as the geology, so I don't want to spend too much time on those maps. But I do want to highlight, the water quality piece of this, or water chemistry piece. And as much as we all want pure drinking water or pure water, it's important to point out that in the natural environment, in the natural world, we never find pure H2O. Water has a really unique and great ability to dissolve those things that it comes in contact with. So those things would be the types of rocks or minerals that water is stored or transported in, the types of land use where that water soaks into the ground. Even the types of plumbing and packaging that water is stored or transported in will impart different impurities to that water. So if I say Flint, Michigan, what do people think of? Lead. So that's a pretty tragic example of how the municipal plumbing system was the source of the lead contamination in that community. That community switched water sources. They did not add the right anti-corrosion agents to that water. And as it moved through that distribution system, it started to eat away or peel away at scale, exposing years of accumulated metals and minerals from that plumbing system, which caused a lot of people to suffer health complications from that particular incident. If we do find stuff in our water that is unpleasant for aesthetic reasons or may cause health issues, just know that there's oftentimes treatment. We can talk about well construction sometimes and how that might improve water quality, but a lot of times that might be an expensive experiment. We don't always know if that's going to result in better water. So treatment can be a very cost-effective option if people have impurities that they don't want or they want to remove. When we look at the tests that we ran, there's different categories of tests. Also important to point out that some of these come from rocks or soils. Other of them are impacted by land use impacts or things that humans might do. And some of these are important to health. There's other tests that we include because they impact the taste, color, and odor, which are reasons that might prompt somebody to want to know or submit a water test. And then there's other tests that tell us things like, how is that water going to interact with my plumbing system? That can also be very important to know about. When we talk about health concerns associated with well water, I think it's important to distinguish between acute effects. Those would be effects seen within short time of exposure to a particular substance or pathogen, things like bacteria or viruses, which cause foodborne illnesses. Or if we think of things like Giardia or Cryptosporidia, those are examples of acute effects where shortly after exposure to those pathogens, usually hours, maybe days afterwards, people develop symptoms. Those are acute effects. And then we have chronic effects, things like arsenic or pesticides in the water that we know at elevated or increased levels will increase the risk of developing health complications from using that water as a drinking water source. But it's not from using that water once or twice. It's using that water for probably years or decades at those elevated levels that would cause some sort of health complication from that water source. So really, I think useful to know that if we do find things like manganese or arsenic into the water, there are some maybe preventative steps that we want people to take, but it's not a guarantee of health complications. We're looking to find ways to help people reduce the risk that those health complications may develop. Also important to point out, there's differences between public water supplies and private water supplies. I grew up in Milwaukee. I live in Stevens Point. Every time I turn on the faucet, I am very confident in drinking that water because I know the water utility bill that I pay quarterly goes to pay a staff that regularly tests that water, maintains the infrastructure. If there's anything wrong with that water, if it doesn't meet drinking water standards, that municipality is required to treat it to make sure it's suitable as a drinking water source for or according to drinking water EPA standards. Private wells are often, people are surprised, are not required to be regularly tested. The DNR regulates well construction. They don't actually regulate water quality coming out of those wells. So unless the individual homeowner has taken it upon themselves to do routine testing, that is not likely going to happen on its own. If we do find anything wrong within those test results, you are not required to take any sort of further action. We want to make sure that at the end of today, if you have something wrong with your water, we want to give you the appropriate information to know what those next steps might be. But we are not going to follow up with you to say, hey, we noticed this. What did you do to make your water quality better? We have no ability to force you or require you to do anything, but part of my role is to make sure you know what those next steps might be. Just real briefly, this picture is what your well probably looks like. That metal pipe that sticks out of the ground is what we see, but just know that there's a lot going on below the ground. All the maps that Elmo and Amy showed show how complicated our soils and geology are. And it would be great if we could stick a camera down each well and get a visual of what that actually looks like. This is oftentimes all that we're able to view when it comes to our well, but there's a lot that each individual homeowner can do to try and make sure that it's providing the best or the most sanitary water possible. Ensuring that that cap is secure, that it's a vermin-proof cap, that it's keeping insects and other unwanted rodents out, making sure that casing extends a certain distance above grade, making sure we keep that area relatively free and clear of debris and other obstructions, taking care not to hit it, maybe with our cars or the snowplow. We want to pay attention to the downspouts and how that water from rooftops or runoffs is being routed through our yards so that it's not being accumulated or ponded directly around that casing. There's some easy things that every homeowner can do to try and ensure the best, most sanitary water supply possible. Then there's this question we always get, do deeper wells mean better water quality? And well depth is important, but casing depth and screen depth is equally as important for determining water quality, right? So in this diagram, the black lines represent the casing depth. The white area represents the total well depth. If the casing only extends to the top of the water table, it means that whole lower section of the aquifer is open and water can enter that well along the whole opening of that well borehole. If we deepen the casing, we seal off that upper portion of the aquifer. We're pulling water from deeper. It doesn't mean that water can't become contaminated, but by pulling from deeper, it takes longer. It's not as easy a pathway for water in this type of geology to get down to that level where it might be problematic for somebody's well. This is just another way to think about the role of well depth or screen depth, in that shallow wells are accessing water that's closer to the surface. It's more impacted by the things that are happening on the landscape nearby, and that water tends to be younger in age. Most private wells, most kind of sandpoint wells are probably accessing water that recharged or infiltrated within a quarter mile of that well. So if we think about what's happening on the landscape, the land use near that well, those are the things that we have to worry about in terms of impacting our water quality. And it's not going to take very long. Most sandpoint wells are probably accessing water that might be years, maybe a decade old. We'd like to think that we're all drinking glacial meltwater, but the truth is that most instances that's not the case. One of the first things we'll talk about is hardness. Hardness is the measure of calcium and magnesium. It's naturally occurring. There's no health effects. Actually, calcium and magnesium are somewhat beneficial to health. The amount we get from our water is small compared to what we should be getting from our diets. But when it comes to the problems with hardness, too much causes kind of scaling, soap scum. People with hard water tend to use more detergent. And that scale on a heating coil of a hot water heater may decrease the efficiency of that device to heat water to the proper temperature. Levels greater than 200 are considered hard water. That's the level at which people would probably choose to install a water softener. We have like this level between 150 and 200, which we consider to be kind of an ideal range. And then less than 150 is what we consider to be soft water. Water with a low mineral content means that that water tends to be a little bit more aggressive or corrosive, which can be problematic for metal plumbing. If we look at where we find hard water or the differences in hardness concentrations in Burnett County, what you'll see is the blue dots are wells that measured less than 100 parts per million or milligrams per liter of hardness. And that's about 51%. Just over half of the wells are less than 100. We have another roughly half or so that are 100 to 200. And very few that are above that level. So when we talk about water softeners or the need for water softeners in Burnett County, they are not going to be as common as we might expect in other parts of the state, like eastern Wisconsin, which may have hardness levels of 300 or 400 milligrams per liter due to the geology and the soils that they have there. In general, when I look at this map, I'm seeing that the northern and the western portion of Burnett County generally has lower hardness levels than the southern half or so of the county. And then that's most likely related to some of the things that Elmo showed in terms of where those deposits came from, when those glaciers scraped across the landscape, what sediments did they carry with them, likely has a pretty significant influence on this particular parameter that we looked for. Water softening can be very effective for removing hardness. It has some ability to also remove iron and manganese. But when it comes to iron and manganese, water softeners are not going to be as effective as other treatment for dealing with these elements. If we have small concentrations, this might be effective, but larger concentrations, we might be better served by installing some sort of oxidation or iron filter. But water softeners, how they work is they remove calcium and magnesium. They may remove a little bit of iron and manganese, and they add back in a little bit of sodium. So for people that have water softeners, if you're drinking softened water, just know that you're increasing your sodium intake a little bit. If your doctor says to limit your sodium intake, then drinking softened water might be something that is important to note, and try to reduce sodium intake if possible. The other things that I'm going to highlight next are related to land use. So starting with nitrate, nitrate is a test that's important to health. It's one of the more common tests that people perform on a water supply. Levels greater than 10 milligrams per liter are considered unsafe for infants and women who are pregnant. And we encourage everyone to avoid long-term consumption of nitrate greater than 10. Nitrate is also a great indicator of land use impact. So levels less than 1 are kind of considered background or natural levels of nitrate in Wisconsin's groundwater. Those are levels that we would expect to find if humans weren't farming, if humans didn't have septic system drain fields. These are the levels less than 1 that we would expect to find if we weren't here. Health effects related to nitrate: methemoglobinemia. The common name is blue baby disease. That's a potentially fatal condition in infants less than 6 months of age. There's also links to birth defects and miscarriages, not only in humans, but also in livestock. And then it's also a great indicator of other contaminants. So the question about pesticides, if we're in an area with elevated nitrate and the source of that nitrate is agricultural fertilizers, then it might be more important to test for things like pesticides. If the nitrate is elevated and we assume that that nitrate is coming from a septic system drain field, might be more important to test for things like pharmaceuticals or personal care products that would be associated with human waste distribution systems. When we look at the nitrate, there's some really good news for people in Burnett County in that when we look at less than 2, we'll just say that things less than 2 are natural or background levels. That accounts for 91% of the water samples submitted are at background or natural levels. There were 6 samples under 1% that were considered unsafe or unsuitable as a drinking water source. This is not typical of Wisconsin. If we were to test all the wells in the state of Wisconsin, we might expect about 10% of them at any given time to exceed that drinking water standard. And here in Burnett County, you're looking at less than 1%. One of the really important things about the work that Amy and Elmo are doing is that groundwater susceptibility map, highlighting which areas are susceptible to certain land uses. And then we can look at overlaying that land use information, which helps better explain why we're seeing some of the things that we are. So knowing that agriculture is a primary source of nitrate to water, it's no surprise that in the eastern portion on the left here, where we have more intensive agricultural activity, if we look back to that nitrate map, that's the area where we see some of the highest concentrations of nitrate. We have this other area of fairly intensive agricultural activity down in the southwestern portion of the county, but we don't have as much evidence of nitrate making it into those wells. But when we think about the geology and some of the maps that Amy showed, the recharge in that part of the county is much less due to some of those glacial tills that result in more water running off than is infiltrating down into the groundwater. So I think that's one of the reasons why the nitrate map looks like it does, even though we have land uses that would be expected to release nitrate to groundwater, the soils and the geology are limiting how much actually makes it down into people's wells. If we look, just again, highlighting statewide, this is showing all of the information that we know for the state of Wisconsin. It's averaging the concentration by those grid cells. The empty grid cells are areas where we don't have sufficient data. But what you'll see, and if you remember, what we're looking at is the lighter colors, the light yellow or orange would be low levels of nitrate. The darker the orange, the darker the reds, the higher the concentration of nitrate. You remember Amy's statewide groundwater contamination susceptibility map. Northern Wisconsin is extremely susceptible. Its groundwater is really susceptible to land use activities. But the reason we're not seeing all the nitrate in the groundwater is that we have a lot of forested acreage. Forests are great for water quality. And as a result, even though this landscape is vulnerable, a lot of sand and gravel aquifers, it's the land use that's really keeping them, quite good with respect to nitrate and some of the other land use characteristics that we commonly look for. Chloride is very similar to nitrate in that naturally we'd expect these levels to be low. We'd say less than 10. Greater than 250, it can give water a little bit of a salty taste, but there's no direct impacts to chloride, elevated levels of chloride on health. It can just cause some aesthetic or corrosive concerns at really high levels. Sources of chloride are going to be fertilizers, septic system drain fields, humans intake a lot of salt. We excrete a lot of salt in our waste. So that gets deposited to the septic system drain field and can eventually find its way into groundwater. And then in the winter months, the road salt that we apply to de-ice our roads can get into the ditches. And then in springtime, that water melts and soaks down into the ground, carrying some of that chloride with it. If we look at the chloride map, what we'd see if we look at background or natural levels and add those up, we're talking about 84% are at those background or natural levels, very similar to what we're seeing for the nitrate. Little evidence of significant land use impacts to groundwater quality in Burnett County, even though you have a lot of shallow wells. the groundwater quality is quite good. Again, I think mainly because of the land use, dominant land uses that you see here, combined with some of the soil characteristics and geology. Other things that we looked at, alkalinity, conductivity, pH. These are things that help us measure the corrosivity of the water. We can put these into a calculation that tells us the aggressiveness of that water on particularly metal plumbing. People are probably familiar with pH and that it's water acidity. Common pH levels in Wisconsin are between about 6 and 9. The human body can tolerate a wide range of pHs, so we're not really concerned about pH from a health standpoint. It's more concerned about pH from what it does or how it interacts, how it causes that water to interact with our plumbing. Alkalinity, notice the map shows low levels of alkalinity in the north, higher levels in the south. This mimics the hardness map really closely because alkalinity and hardness essentially originate from the same source. If we look at conductivity, this map follows very closely the alkalinity and the hardness. And then if we look at pH, it's a little bit harder to see, but we do generally find lower pH in the north and slightly higher in the south. I do think it's important to point out that the lab pH, the pH that we measured, is always going to be slightly higher than the pH coming straight out of the faucet. So if you have treatment people coming over to your home and taking a pH measurement, it's going to be typically 1 pH unit lower than what we might expect to find when we measure pH in the laboratory, because the longer it sits, the more CO2 vents off or out of that water sample, and the higher the pH gets. Similar to uncorking the top of a bottle of soda. When you do that, you see the bubbles, the CO2 venting off. Essentially, the same thing can happen with people's well water. It's just you don't always see the bubbles. Occasionally, I will get calls from people saying that their water is fizzing, and that's usually what people are viewing when that happens. But the reason we did those tests are that we can use them to calculate the saturation index. Negative values mean corrosive water. Positive values are more likely to form scale. And the more negative, the more corrosive. This is showing us the areas or the dots that are black, purple, red, or orange would be considered to be aggressive or corrosive. The blue and the green would be kind of balanced water. So why is this important? People with corrosive water, if you do have metal plumbing, particularly copper plumbing, or older homes with copper plumbing and lead solder, you might be more prone to pinhole leaks or higher elevated levels, unsafe levels of lead or copper in your drinking water. And that's just a result of the inherent properties of the groundwater, the well water that you're accessing. I mentioned copper. The standard for copper is 1.3 milligrams per liter. So again, water sitting in contact with copper plumbing can sometimes dissolve unsafe levels of copper, causing things like stomach cramps, diarrhea, vomiting, or nausea. And then lead, prior to 1985, they used lead solder to join together copper plumbing. Lead is also a component of brass. So occasionally someone that sampled from a brass fixture will notice really high levels of lead. Notice that standard 0.015 milligrams per liter, that's a really small number. There's no known benefits to lead in the human body. So the more we can reduce our exposure to lead, the better off all of us will be, particularly young children. As serious as some of the health effects are with lead, fortunately, letting the water flush through the system, instead of turning on the tap when you wake up in the morning and taking a drink of water, let that water run for a minute or two before filling up your water bottle, is one way to reduce exposure to elevated levels of these two elements. Arsenic is another test that's important to health. Here in Wisconsin, we have some of the highest concentrations anywhere in the world. In eastern Wisconsin, you'll see that red band, particularly along the shore of Lake Winnebago. There's a certain geologic layer that's really high in arsenic. Occasionally, we'll find arsenic at elevated levels in other parts of the state. So as a result, the DNR recommends every well be tested for arsenic at least once. That standard is 0.010 milligrams per liter. You'll notice some of the health effects listed here, mainly certain types of cancers that can develop from long-term exposure to elevated levels. The good news is that arsenic doesn't appear to be very common in Burnett County. Of the 450 samples, 98% were not detectable. They detected levels less than 0.005 milligrams per liter. That's the lowest most level that our equipment is able to pick up. And of those that did detect arsenic, only 2%, or I should say 2% detected some level of arsenic. None of them were considered unsuitable or above what's considered acceptable from a drinking water standpoint. These are more likely to be the common complaints or problems that people here in Burnett are experiencing. So iron, which causes that reddish brown staining, is naturally occurring. It's more likely to occur in places like northern Wisconsin, where we have a lot of lakes and wetlands. A lot of organic matter in the soils or the sediments will exacerbate or make iron more soluble in the groundwater. And then when it comes out of the pipe, that water comes in contact with oxygen, and that iron starts to precipitate out as a sediment, or maybe that film, that red stain on your white fixtures or on your laundry. Very similar. Well, here's the iron map. And unlike some of the other ones, which have maybe some easier to describe patterns based on where you're at in Burnett County, iron is a little bit harder to describe. Although when we look at where some of the highest levels occur, it's oftentimes in the areas where we find more wetlands or higher water tables, indicative of low oxygen water, or water that may not be moving through the landscape as quickly, where it tends to have less oxygen, and it's going to be more capable of dissolving iron and manganese from the soils and the rock that it flows through. If we look at manganese, manganese is very similar to iron in terms of where we expect to find it and the conditions that cause it to become elevated in the groundwater system. We have an aesthetic level of 0.05 milligrams per liter, which is where we'd expect to find water with black or maybe brown precipitates forming. That picture you see in the upper right is the picture of a toilet tank. And there's a fine black sediment in the bottom of that, which would be indicative of manganese precipitation. And then when we get levels above 0.3 milligrams per liter, there is some health concerns associated with that. Long-term exposure may harm the nervous system. It's been described as having impacts of Parkinson-like symptoms for certain people that are drinking water with elevated levels of this particular element, manganese. And both the iron and the manganese, if we look at the statewide maps, you'll see these two elements are much more common in northern Wisconsin than they are in southern Wisconsin. And it's a byproduct of the materials, the geology, the pH, and other factors related to the groundwater system in this part of the state. Here's the manganese levels. It's difficult to see, but if you look at the maps, once they're put online, you'll see similar kind of patterns in terms of where we find the highest concentrations of iron and manganese, oftentimes overlap in nature. So in summary, when we look at what we've learned from testing of these wells, Burnett County groundwater shows less impacts from common land use concerns, i.e. nitrate and chloride, than we generally see statewide. I think a lot of it has to do with the land use that we find here, combined with some of the soils or the geology information that we're learning from the study. There's generally low mineral content, which is going to make water naturally more corrosive or aggressive. The iron and manganese that contribute to staining and other aesthetic concerns are probably the most common problem or complaint that we would expect to find from well owners in Burnett County. And then when it comes to arsenic, which is an important test to perform, good news is that there's a low probability of finding significant arsenic in private wells in this part of the state. What I'd like to leave people on is just 3 basic points for any private well owner, which is periodically inspect and maintain the area around your well. We'd encourage people to test regularly to evaluate common water quality concerns. And if those test results indicate any sort of issue, at that point, it might be necessary to take some sort of corrective actions or next steps. In closing, before we open it up to any questions for me or questions for the other presenters, I do want to thank all of you that submitted samples. This information in terms of the water quality would not be possible if it weren't for all of you sending in samples from your wells. The Burnett County elected officials who have agreed to support the project through various county funding sources, as well as the Burnett County Land Conservation Department, which did the bulk of the work when it came to communicating with all of you, recruiting you, and initiating this project. So with that, I will just offer up for Dave or Emily, are there any last minute comments or things that we forgot to mention before we open it up for some questions?
I don't think so offhand. I think we could open up for questions. Looks like there's a bunch of them. And you might want to address the depth of wells with the iron manganese, because that seems to be a common thing around here. If they have shallow sand points, that you have more of an iron issue.
Yeah, when it comes to the depth of the well, especially in areas with a lot of lakes or wetlands, the organic sediments, especially in wetlands, are going to be deposited in those types of ecosystems. Lots of organic matter results in consumption of oxygen from that water, and those low oxygen conditions will tend to dissolve iron and manganese from the sediments that it's moving through. Therefore, if your well is shallow and closer to those water resources or those sediments, it's going to be much probably higher likelihood that those conditions are going to be existing in those shallower zones. Sometimes if you go deeper, you'll access different types of sediments where the water characteristics aren't as conducive to dissolving high levels of iron and manganese. So if you're going from a 30-point sand or 30-foot sand point down into a 100-foot well into sand and gravel, it might be possible to kind of drill your way out of some of the water quality problems that you have. I always do tell people it's an expensive experiment, though. No well driller is going to guarantee you better water. So there's oftentimes the best thing you can do is talk to your neighbors, see what they know about their well construction, their well depth, ask them how they like their water quality or what types of water treatment they have installed. Talk to well drillers that are knowledgeable about the area to ensure that drilling deeper is truly going to make a difference in terms of the problems that you might have. But well depth, shallow versus deep wells can make a difference in terms of water quality for sure.
What if you're not drinking it? How?
So great question. So the question is, what if you're not drinking the water? How could I phrase it as, what if you're not drinking the water? How important it is to test? If you're not drinking it, then, and you're happy, generally happy with it, then we're not as concerned, right? If most of the things that we're talking about, things like nitrate, arsenic, manganese, they're going to be drinking water issues. If you're using it for bathing, for showering, for washing dishes, that's not going to result in health complications. So unless you're concerned about it for aesthetic reasons or drinking water safety, then you may not need to test because the things we might expect to find are not negatively impacting you or you're dealing with it by avoiding it. Avoiding, drinking that water. So it is, anytime you're on a private well, it's really a personal decision whether or not you choose any sort of corrective action for a particular problem. There's some people that, have hard water that don't have a water softener because they might notice a little bit of scaling, but it's not bad enough for them to go out and install a water softener. There's other people that, if they have a little bit of cloudiness on their dishes, it's worth it to them to install that device and eliminate those issues or those problems. We just want to make sure that if people are drinking it, that they're informed about that water, and that if it does exceed certain levels, that they know what corrective measures they can take.
Excuse me, we submitted a water sample and didn't receive results. What should we do?
So for anybody online that submitted a water sample but did not receive their results, occasionally things will happen where it gets lost in the mail and we will never know. Sometimes we get them sent back to us because we may have entered an address incorrectly. If you did not get your result, please send me or Emily an email or give us a call, and we can reprint your results and mail them out or email them to you as well. Email is oftentimes a little bit quicker and faster, and it's less prone to getting lost in the USPS system.
Great,
So
thank you.
apologies for that, for anybody that did not receive them, but we do want to make sure that we can get them to you.
Questions in the chat.
Question back here.
Our results indicate that you don't have a problem with nitrates or iron or lead. Everything's real low. And yet, not to be too crude, we cleaned the toilet and within a day or two, it's growing stuff in there again already. It's like, what the hell? If nothing's indicated on this sheet, why it's so quickly and easily growing things?
Yeah, so the question was
We do filter the water with just a little Brita filter, and I think every time I drink a glass of water, it's like, what the hell am I drinking?
Yeah. So the question is about, the water quality results generally look pretty good, but yet you're still noticing some biofilm or some bacterial growth maybe in the toilet bowl or toilet tank. And
we don't have a problem with iron on porcelain or anything like that. Nothing like that.
Yeah. And if you think about it, municipal water systems, generally the vast majority are adding chlorine or some sort of residual disinfectant that exists throughout the water supply, which would, if water becomes stagnant, it's making sure that those bacteria, those biofilms aren't growing. In a private well, you're not adding any sort of disinfectant. So if naturally you're in an area with a lot of organic matter, even though you might not have high iron that would cause, let's say, iron bacteria, there might be other naturally occurring bacteria in that water supply that exist and can take hold. If that's happening, one thing that people can do is periodically disinfect their well water system. A lot of times what you'll notice is I'll get calls where it's like, well, we've been using this well for 5 years, but this last year, the problems, the slime, the buildup has gotten worse. And that can happen in a well where, it's clean, but over time, those bacteria start to grow and eventually reach a point where they're being drawn into the plumbing system and in your house. Under those conditions, it can be really difficult to completely get rid of that issue or that problem, but you can periodically control it through periodic disinfection of the system. So that might be one thing to try, is to perform maybe wait until spring or summer, perform a well disinfection and see if that gets.
Plumber's job, or is that a well digger's job?
It's usually a well driller, a pump installer. The DNR does have a procedure that homeowners can choose to do online. There's certain products that are for sale, at Menards or online, that some people will use as well, different types of pellets that you can put down the well, that will try to clean it out. Given the situation you described, that's the first thing I would try a well disinfection. See, one, if it helps, and if it helps, make sure you track how long that lasts, how long that benefit lasts, because that would give you some indication of maybe how often you want to perform that so that it doesn't take as big of a foothold on the system. If that works, then repeating that every so often might be one way to avoid that in the future.
Thank you.
So that would work for me that doesn't drink the water too?
In terms of work are you noticing kind of slime or
No, not yet.
yeah, if anybody notices kind of like that there's iron bacteria would cause kind of a slime or an oily sheen on the water. It may cause off-putting odors. Some people say it smells like sewage, like rotten eggs occasionally. If it's related to iron or sulfate reducing bacteria, then disinfection may be one thing that could help. You could try that, but it's not going to eliminate the problem. It's a way to control it.
I got a couple questions in the chat. Zachary asks, we're in Webb Township in northern section of the county. We have a Sandpoint well, and I'd like to learn a bit more about them. For example, how deep do they tend to be? What are their pros and cons? And would you advise against them if I need a new well?
So Sandpoints, not everybody in the state, Dave and I were talking about this, not everybody in the state would be able to install a Sandpoint, right? In order to have a Sandpoint, you need sand and gravel aquifer. You need the water table relatively close to the surface. If the water table is really deep, the Sandpoint is not going to give you access to adequate water. So where we find them are areas where we find a lot of sand and gravel, water tables relatively close to the surface. Most of the time, they're not going to be more than probably 40, 50 feet deep. A lot of them will even be shallower than that, 20, 30 feet. When it comes to shallow wells or shallow Sandpoints, some people think they're illegal. They're not illegal. And if I had a property with 40 acres of forest from a land use standpoint, I might love a Sandpoint well because I can control my recharge area. I know what's being grown. I know where that water is coming from. And if I protect the recharge area, the capture zone for that well, I might really value having a shallow Sandpoint well. So there's nothing inherently wrong with them, but the drawback or the con is that they do access water that tends to be younger. And if you're in an area where you don't control that land use, or the land use is being impacted, you're typically going to see higher concentrations from those activities. They're not benefiting from the longer flow path and the dilution that might result from that integration of recharge from larger areas. And the water tends to reach the well faster than it would if it were drilled deeper. So there are pros, there's cons, and it totally depends on where you live and what the land use and the geology is in your immediate vicinity. I wish I could provide a more black and white answer, but unfortunately a lot of times we're putting in a lot of caveats because it's site specific.
From the same Zachary, he also wants to know how many Sandpoint wells were included in the study.
So the question was how many Sandpoint wells were included in the study? And I do not know that off the top of my head. I think that could be a next phase of the project is to look at things like well depth and how that well depth might relate to the water quality. knowing, you're categorizing the water quality by sand points versus drilled wells could also be a great, interesting question to investigate further, but we don't know that right now.
Is PFAS a risk in our area?
So the question was about PFAS. This is in the news a lot. Perfluoral alkyl substances, non-stick coatings, firefighting foams are the source of PFAS. It's in food packaging. We'll likely find it, if we look for it, which we did, we worked with the DNR on a statewide study. We found it more frequently than we probably thought we would, at very low levels. So the frequency of finding it above drinking water standards was low. But the risks, or the reasons why wells were more likely to have it, we kind of linked to areas where biosolids, municipal biosolids or paper mill sludge may have been spread, or stored on the landscape. Areas where you have a large, or a lot of drain fields, septic drain fields in close proximity to one another because of all the nonstick coating, the waterproof fabric that we're washing in our laundry machines, the food packaging, that goes to our drain field. That can be a reason why we might expect to see elevated levels. And then obviously, if you're in an area where there's been a structure fire, or airport where they've used firefighting foams, those would be other reasons why you might want to test for PFAS. If I lived in the middle of Burnett County, and my nearest neighbor was, a couple 100 yards away, I probably wouldn't spend the money at this point to test for PFAS. There are people that I think would be more likely or would benefit more from PFAS testing, but I think the vast majority of people in Burnett County, it's not something I'd say is high priority.
Our Sandpoint well is located in the crawl space under our cabin. Is that a problem?
So the question was about the well located in the crawl space below the cabin. So that would be an example of a non-code complying well. If it's below grade, my guess is it's below grade. If it's a crawl space below the cabin and it's not below grade, then that's maybe more of a gray area. If it's in the basement or it's below grade, then the risk is that if we have a flooding event, that low space, that crawl space is going to be the first thing to be inundated. And if a well is inundated, then you have water from the surface flowing into your potable water supply. So for that reason, they no longer allow wells to be installed in basements below grade. So it's a little bit of more information would maybe be necessary to say for sure, but based on the description, it sounds like it might be a non-code complying well. Nobody is going to cause or come over and say you can't use your water or use that well. But where it becomes an issue is if you go to sell that property and somebody does a well inspection, then the lending institution would probably not agree to purchase the property or loan money for that property because it's a non-code complying structure, and that impacts the price or the value of that property if it needs to be replaced at that time.
I have high levels of both iron and manganese. What can I do? I don't have a sand point. The manganese is plugging the jets on my tub.
So the question is about high levels of iron and manganese. It's not a sand point. What do you do about it? If you have not tried treatment, that might be the next step. There's well kind of disinfection procedures that you could try and clean out. Again, with iron bacteria, sometimes those problems can build and grow. And if you're not periodically disinfecting or cleaning, then the problems just keep getting worse and worse. But my guess is based on what's described, if you don't want to explore drilling a different depth well, and in this case, it doesn't sound like it's a shallow well. So it's uncertain or unknown whether going deeper than they currently are would make a difference. But exploring drilling a new well could be an option. Otherwise, treatment is really probably the one way that you could, if you haven't tried that, that would be the next step to investigate. Unfortunately, I mean, it'd be great if we could say anybody could drill a well anywhere in the state of Wisconsin, get water that was safe to drink and didn't have any aesthetic concerns. But when we look at northern Wisconsin, iron and manganese, we know are problematic throughout the Northwoods. And just certain geologies, certain regions are going to be even more susceptible than others. So it's one of the realities of living in the Northwoods. There's a lot of great perks and great benefits in terms of the scenery, the aesthetic beauty, the access to natural resources. This might be one of the things that we have to live with to live in certain areas.
2 more questions. This one was also similar to the 1 o'clock question, is what are the well water impacts from the Superfund site and at what distance from the site?
So we had a question about the Superfund site in the morning or the afternoon session. I do not know a lot about the Superfund site, so I don't know what particular contaminants we might be looking for. I can say that the things we looked for in this baseline testing that was offered would not probably pick up the chemicals or impacts from that Superfund site.
It's pentachlorophenol and chemonite.
We definitely would not pick up or see any influence or difference in our results, even if those wells were in the area of the Superfund site. But that being said, the question about how far away would you expect those things to go? You know, when we talk about landfills, there's some recommendations of testing if someone lives around a landfill. Things like volatile organic compounds, some of the things Dave talked about are examples of those. We usually say wells within a quarter mile of a landfill should be tested for those compounds. I think people are often surprised that once you get beyond a quarter or a half mile, we're not likely to see significant impacts from those activities. When it comes to known spill sites, the DNR oftentimes has data that they've required of the offending party, where they've worked with environmental consultants to install monitoring wells to identify where that plume is, how far it's extended, and then monitor it to make sure that it's being cleaned up. So if there are known spill sites in Burnett County, the DNR does maintain a database, a mapping platform on their website. It's called BRTTS on the web, where you can search for some of that information and might be able to learn more about what water quality data has been collected and what the status of that investigation is, whether it's open and ongoing or whether it's been closed.
My last question in the chat, where can well depths be found?
The question is, where can well depth be found? And Amy mentioned the well construction reporting database on the DNR website. So if your well was drilled after 1988, that information is really easy to find. After 1988, every new well would have been assigned a Wisconsin unique well number. It's a 2-letter, 3-number code that can be entered into that website, and it pulls up that well construction report. Prior to 1988, there are ways to find it, but it becomes much more difficult. And there may be some wells that, just based on the record keeping back then, are not able to be found. Searching Google or your favorite search engine for Wisconsin well construction report database would be the easiest way to get access to that resource, to find your well depth, screen or casing depth, as well as what types of materials. Elmo mentioned using those logs to figure out the types of materials that wells are drilled into. That information is also located on that report and can be really useful to have on hand.
And that's all I got on the chat.
Made it through all the questions and sure. What?
months, I'm grateful that the Burnett County government is concerned about water quality and still facilitating the study. That's wonderful. And, the Burnett County just completed a 10-year plan, and I assume in 10 years there will be another plan. And I'm wondering if there might be a trajectory that some sort of way of looking at the trends with respect to land use and the expected effect on water quality will be available. In 10 years, will we have a much better ability to look at this data and use it to come up with a plan that anticipates changes in land use?
So I'll try to start answering that question, and I might turn it over to others. But for those that are listening online, it was asking about this question of trends or understanding land use changes and how in the future those land use changes might impact water quality. Would that be a correct summary? And you also, said you were appreciative of the elected officials, and I would encourage everyone that thought it was a great program to make sure you tell them that. I think they'd probably enjoy hearing that. I know their department, the Burnett County Land Conservation Department too, had a big role to play in that, and helping them understand how valuable you found this opportunity, I think is really oftentimes important for people to hear. But with respect to that question of trends, I go to a lot of communities, and they want to know if their water quality is changing over time. And some of them don't have any information as a starting point. So the fact that Burnett County did this 10, 20 years ago, they did it now, that gives this community the ability to do that. The things that we would expect to change if land use changes from forest to agricultural activity or forest to subdivisions, we might expect things like nitrate and chloride to go up. Right now, those elements look like they're quite low, but routinely doing testings like these to try and assess, how things might be changing is one thing that's possible if you take the initial steps of doing a baseline investigation, which Burnett County has done. So I think you're all set up very well, but it depends on what happens in the future moving forward, whether or not that information can inform those types of questions that you all have. That's a starting point, but unless somebody decides to do it again, then the utility of this information maybe isn't as good at getting at that specific question. Anything to add from Emily or Dave?
I was just gonna say is yes, future land use is tough to predict. But on the other hand, the whole concept of having the one we did in 1990 and now this one allows, as he said, to have a baseline to know exactly what it is and to allow the county boards and the townships to make better decisions on what those land use things are based on the potential for groundwater contamination. And that was part of this discussion. And I think one of the things you mentioned this afternoon you may want to go to is the test that you provide besides the ones that we did through this. And I had something else and I can't remember it.
Yeah, so thanks for asking that question, Dave, about what else could be tested for. What you had tested for was certainly more than most people in Wisconsin know about their private well. Most people might know nitrate. They might know bacteria. Bacteria was not included in this testing, even though it's probably the most important test to do regularly or routinely on a private well. It tests the bacteriological safety or sanitary nature of your water supply. It's a snapshot in time. It's oftentimes related to the well construction, and it doesn't tell us as much useful information about general groundwater quality as it does cite specifically about the well and the integrity of that well water system. It's also very challenging to include in a large testing like this because it's time sensitive. So the mail approach, which was nice to make it really convenient for all of you, would not have been an option if we included bacteria. But that is something we recommend every well test for, we'd say annually. If you can't remember the last time you tested for bacteria, it's probably time to do that. So that's one thing that's available and that's out there. Pesticides, if you live in an area where there's a lot of agricultural activity, you might consider testing for pesticides. I oftentimes tell people to use nitrate as a guide of whether or not to pursue additional pesticide testing. Your nitrate level was greater than 5 and you live in an agricultural area, then pesticides might be important. If it's less than 5, it's probably indicating not very significant impacts from land use, and the risk of pesticides in that incidence is pretty low. So I think that kind of covers it. We talked about PFAS earlier. That might be something else that people want to do and want to consider, and that is also an option as well.
Briefly, our numbers came back surprisingly good and all that. How often should you consider personally, like rechecking? Every 2 years, every 5, every 1?
So the question was about how often should you consider redoing the testing or testing your well? And I'd say annually for bacteria and nitrate. When we talk about things like arsenic or iron or manganese, those might be things that you don't want to test for annually, but maybe every 5 to 10 years. Or if you notice a sudden change in color, taste, or clarity. We get a lot of calls, during droughts as that water table drops. There can be changes to somebody's water quality that they might want a different measure of their iron and manganese level during that time. Or during periods of really wet precipitation or wet periods, the water level rises and people notice changes in the quality of their water. So there may be other reasons that might prompt you to test, but just as a rule of thumb, annually for bacteria and nitrate is typically what we encourage everyone to do.
A couple more come through.
Any other questions, either from here or online or?
Yep, 1 second, Dave. What problems come from nickel mining, referring to water, soil testing effects?
So the question about nickel mining, I'm not a mining expert. So I don't want to talk out of school. Any mining activity, there's different types of mining, and it would depend on the type of mine, where they put the tailings, a whole host of factors. But anytime there's a land use change, there's probably always water quality considerations that we want to be mindful of, but I'm not knowledgeable enough on that question to talk.
Yep. Where can you send tests if they are time sensitive?
So the test that would be time sensitive would be bacteria. The time between when a sample is taken and when it needs to be analyzed or set up in a laboratory is usually about 40 hours. So we do get samples at Stevens Point that are submitted through the mail, but they're usually submitted overnight through FedEx or USPS. So it is possible. It just costs a lot more sometimes to do that. There are local labs. I know Sawyer County has a laboratory that does bacteria at their local health department. I believe there may be other labs locally that the state maintains a listing of certified bacteria testing labs on their website. And there may be other labs locally that could help with that. But when we're talking about time-sensitive tests, really bacteria is the one that's most critical. All of the others you could, Stevens Point does a wide variety of those elements. The State Lab of Hygiene down in Madison is another laboratory that tests for a wide variety of things. There's a private lab, Northern Lake Services out of Crandon, that also has a pretty extensive list of testing options that they offer and would mail out a kit and people could send back.
Yeah, the Burnett County Health and Human Services has a bacteria kit that you can get. I don't know what the cost is associated to that, but they have bacteria, nitrate and fluoride. They're up on the second floor if you guys wanted to do bacteria.
So thanks for mentioning that. And they do that in-house?
I think so.
Cool. So that's by far probably your most convenient option when it comes to bacteria testing.
To do it here?
Yes.
Yeah, because it's time sensitive, so if they do it in-house, which I think they do, then it would work perfectly. You just go upstairs and go to the Health Human Services Department and they should be able to give you a kit. I don't know what costs associated with it. You'd have to ask the gals up there, but we do offer bacteria. Well, it's a little after 8. All the rest of the comments are thanking you guys for your presentations and water is important, all that stuff, so I think we could wrap it up there. The weather is kind of iffy, roads are a little bit slippery, so feel free to reach out to these guys if you have any additional questions, and I just want to thank you guys for coming and spending the night with us.
I'll be around for a little while if you have any questions now.